Welcome back to the Deep Dive. Today, we are going to strip away the glossy marketing of the smart world and look at the rusty, potentially failing infrastructure underneath it.
Right.
I mean, you know the pitch, right? We've all heard it. Smart cities where traffic lights optimize flow in real time, autonomous drones that can, smell smoke before a fire starts.
Cameras that don't just record crime but prevent it. It sounds inevitable, like it's just around the corner.
Exactly. It sounds like sci-fi utopia. But if you talk to the engineers who are actually trying to build this stuff, the people really in the weeds, they aren't talking about utopia. They are panicking about the battery.
It really is the silent killer of the Internet of Things. We have these massive ambitions for, ubiquitous intelligence, putting a digital brain in every device.
Right.
But we're trying to run that brain on a tiny coin cell battery that needs to last for months, maybe even years, without a recharge.
And that disconnect between the dream of smart everything and the reality of just dead batteries is where we are living today. So we've pulled together a stack of research that proposes a pretty radical fix. We are looking primarily at a doctoral thesis by Isaac Sanchez-Leal, specifically focused on partitioned deep neural network inference.
Which is a mouthful, but stick with us because the concepts in there they're game-changing.
And because algorithms don't run on thin air, we're pairing that thesis with some gritty technical documentation from the AI Chip Corporation.
On power governance.
Exactly.
It's a great pairing. The thesis gives us the math to sort of break the rules of data transmission, and the AI chip docs give us the hardware reality of keeping the system from crashing when physics gets in the way.
Okay, so let's set the stage. Why is this so hard? I mean, I have a smartphone in my pocket. It has a battery. It runs AI. It recognizes my face. Why can't we just shrink that down and slap it on your tree? It
comes down to what we call the energy wall. To make a device truly smart today, you need to run deep neural networks, or DNNs. And they aren't simple calculators, they are heavy mathematical beasts.
Okay.
So if you try to run a full modern DNN on a tiny microcontroller, what we call the all-in-node approach, you just hit that wall immediately. The chip is too weak. It burns through the whole energy budget on a single frame of video.
So the brain is just too big for the body. The device dies of exhaustion. Try to think.
That's it.
Okay, so the logical next step is the cloud.
Right.
We do this all the time. Make the device a dumb eye, stream the video to a server, let the server do the heavy lifting, and send back the answer.
The all-in-server model.
Right.
And that's the industry standard, but for the IoT, it has a fatal flaw. The radio. The research in our stack is really clear on this. It shows that wireless transmission, whether it's LTE, LoRa, or Wi-Fi, is just shockingly expensive.
Expensive how? Like my data plan.
Energy expensive. Sending raw video data consumes orders of magnitude more battery life than processing it locally. So you're in a double bind.
Okay.
If you process on the device, you drain the battery doing math. If you send the data to the cloud, you drain the battery using the radio.
So both standard options are dead ends. You're damned if you do, damned if you don't.
Precisely. And this is where the thesis pivots to split computing. On paper, it sounds perfect. Do some work on the device, just enough to shrink the data, and then send that smaller package to the server.
Right. The middle ground theory. It's intuitive. It's like peeling an orange before you ship it to save on weight.
It sounds perfect. It's logical. But according to Sanchez-Leal's research, this middle ground is actually a trap. He calls it the structural barrier.
A trap. Okay, you got to unpack that. Why doesn't peeling the orange work for AI?
This is one of the most counterintuitive findings in this whole deep dive. You have to distinguish between, let's say, traditional computer vision and deep learning. In the old days, you'd take an image, maybe turn it black and white, detect some edges, crop it. At every single step, the data size got smaller.
So finding a cut point was easy. The deeper you went, the lighter the load.
Exactly. You could snip the wire anywhere. But deep neural networks work differently. When an image enters a deep learning model, like a convolutional neural network, it hits these early layers that extract features.
And what does that mean, extract features?
It's not just looking at the image, it's creating hundreds of mathematical maps of the image to understand textures, shapes, colors.
I see.
And the research shows that in these early layers, the data volume actually explodes.
Explodes. You mean it gets bigger?
Significantly bigger. The intermediate feature maps, which is basically the AI's internal scratch pad, can be way larger than the original raw JPEG you started with.
Wait, hold it. So to use my analogy, analogy. I opened my suitcase to take some clothes out to make it lighter, and suddenly the clothes expand to the size of a car.
That is a fantastic analogy. Yes, that is data expansion in a nutshell.
So if I cut the network halfway through and try to send that data, I'm not saving bandwidth, I'm actually making it worse.
That is the structural barrier. There is no natural bottleneck in the early layers. You are doing work on the device only to create more work for the transmission. It's the worst of both worlds.
You drain the battery calculating, and you drain the battery transmitting these giant files.
Exactly.
So, okay, the thesis argues that since a natural bottleneck doesn't exist, we can't just find one. We have to. We have to engineer one. We have to force the network to go on a diet.
And a really aggressive diet. The researchers propose a co-design strategy. They realize they can't just tweak the software, they have to fundamentally alter the structure of the AI model itself. They call it active efficiency induction, or what I like to call waist tightening.
Waist tightening. I like that. It sounds painful, but effective. So let's get into the mechanics. It seems like it happens in two phases. The first is extreme pruning.
Pruning is exactly what it sounds like. A neural network is made of filters. Think of them as little detectors looking for curves, or a specific color, or a texture.
Okay.
The researchers found they could just cut out 90% to 99% of these filters in the early layers.
Whoa, hang on. 99%? That sounds like you're lobotomizing the AI. How can it still work if you remove 99% of his brain?
Well, it sounds destructive, I know, but it serves a very specific physics purpose.
Yeah.
By removing those filters, you reduce the math the little chip has to do. But more importantly, it makes the data sparse.
Sparse.
It means the data map is mostly empty space. It fills the feature maps with zeros. And in the world of data compression, strings of zeros are basically free. They squash down to almost nothing.
Okay, I get that. If I have a page of text and I erase 99% of the words, the file size gets tiny. But surely the meaning is lost.
We'll get to how we recover the meaning in just a second. But first, they did something even crazier. Pruning wasn't enough to beat the energy wall. They had to go a step further into something called one-bit quantization.
1 bit.
1 bit.
Okay, for those of us who don't dream in code, explain the significance of that number.
Right. Most computers, most AI models, they think in 32-bit numbers. That allows for huge precision. You can tell the difference between 0.0001 and 0.0002.
Okay.
Even optimized mobile AI uses 8-bit integers, which still gives you 256 shades of gray.
And they went to 1 bit.
Strictly binary. +1 or -1. Black or white. No shades of gray, no nuance at all.
What does that actually look like? If I take a photo and run it through this 1-bit filter, what comes out the other side?
It doesn't look like a photo anymore. If you look at the figures in the documentation, it looks like high contrast digital static. It's a binary mosaic. You lose all the texture of the road, the shadows on the cars, the color of someone's jacket. To the human eye, it looks corrupted. It looks like garbage.
But the file size has to be tiny.
So small that you can transmit it over these weak, low-power radio protocols like LoRa without killing the battery.
So we've solved the energy problem. The stats here are pretty impressive. Up to 17 times energy savings, and nearly 3 times faster system speed.
Huge gains.
But, and I feel like I'm being a skeptic here, surely we've broken the intelligence. If I send a blocky 1-bit mess of static to the server, how can it possibly recognize anything? You said it looked like garbage.
And that is the absolute crux of the entire thesis. The solution is genuinely clever. It's called accuracy recovery, and it relies on an architecture they built called QCNet, the Quantization Compensator Network.
QCNet. How does that fix a corrupted image?
It doesn't fix the image in the traditional sense, it reconstructs the meaning. So the QCNet sits on the powerful server, it receives that 1-bit binary noise. But because QCNet is a deep learning model, it has learned priors.
Define priors for us.
Priors are just learned expectations about the structure of the world. The QCNet knows, statistically, that the edge of a car doesn't just dissolve into static. It knows a person's leg is usually continuous, not a jagged mess of pixels. So it takes that sparse, noisy 1-bit map and essentially hallucinates the missing details back into existence.
Whoa, hallucinates. We usually use hallucination as a bad word in AI, like when a chatbot makes up a fake legal case. But here you're saying it's a feature.
In this context, absolutely. Think of it as probabilistic reconstruction. It's like an archaeologist finding a single bone and being able to reconstruct the entire dinosaur because they know anatomy. They aren't guessing randomly. They're using deep knowledge to fill in the gaps.
So the device sends a sketch, and the server paints the masterpiece.
Ideally, yeah. And the thesis shows they tested this with something called GradCam heat maps.
Right, I saw that. What are those showing us?
GradCam basically visualizes where the AI is looking in an image, and they showed that even after the image was crushed to 1-bit static and reconstructed, the AI was still focusing on the exact same details, like a pair of sunglasses or a car logo, as if it had seen the original high-res photo.
That is a massive conceptual shift. It's what they call decoupling.
Yes, it decouples the energy constraint from the accuracy constraint. You optimize the little device purely for energy, ruthlessly cutting data quality until it's just barely enough.
And you optimize the server purely for accuracy, using all its power to fix the mess.
Exactly. You stop trying to make the edge device do a job it just wasn't built for.
So the penalty for being efficient is basically removed by the intelligence of the server.
Precisely. You get the battery life of a dumb sensor with the IQ of a supercomputer.
However, even if the algorithm is perfect, the math checks out, we still have to deal with the laws of physics. This code runs on silicon, and silicon generates heat and consumes volts.
Right. And batteries are very fickle things.
This brings us to the AI Chip Corporation documents and the idea of power governance. It feels like the thesis handles the software brain, but AI Chip is handling the physical heart.
This is the other half of the puzzle. You can have the most efficient 1-bit algorithm in the world, but if your power supply overheats or the battery voltage dips during a transmit spike, the node just dies.
It doesn't matter how smart the code is if the board shuts down.
Exactly.
The AI chip docs critique the current industry approach as overkill. They say deployment economics don't close at the edge. What does that mean in plain English?
It means we're using Ferraris to deliver pizza. Engineers often stick a powerful GPU on a lamppost because it's easy, it's off the shelf, but it's expensive, it runs hot, and it wastes a ton of power just idling. AI Chip says for real scale, for millions of these things, you need a dedicated power management controller, or AI PMC.
How is an AI PMC different from just a standard battery regulator? Every electronic device has one.
A standard regulator is reactive. It just feeds power until the battery dies or a fuse blows. The AI PMC is proactive. It uses protocols like PMBUS and SMBUS.
Okay, acronym alert. What are those?
Think of them as the nervous system for the electricity. PMBUS is the front end. It talks to the power supply. SMBUS is the back end. It talks to the chips. It lets the power controller act as a governor.
So it's monitoring the quality of the power, not just the quantity.
Exactly. It looks for pre-fault signatures.
Pre-fault signatures? That sounds like Minority Report for electronics.
It kind of is. Let's say the radio is about to send a packet of that 1-bit data. That creates a huge spike in current. A dumb system might just let the voltage sag and crash the whole thing.
Okay.
The AI PMC sees that spike coming, or it detects the voltage starting to wobble, and it can perform load shedding.
Load shedding, meaning it just turns things off.
Selectively. It can tell the neural network to pause for a millisecond or throttle the clock speed to prioritize the radio transmission. It makes sure the system survives the spike.
It treats uptime as the most important metric.
Their whole philosophy is power is the intersection. It's the choke point. They aren't competing on TOPS trillions of operations per second. That's the old metric. Everyone has fast chips now. They're competing on deployability.
Can this thing survive on a solar panel in winter for 5 years without needing a technician to climb a ladder and reset it?
That's the question, and it fits perfectly with the Sanchez-Leal thesis. The thesis reduces the volume of work the chip has to do.
Right, with a 1-bit inference.
And the AI PMC manages the intensity of that work to protect the battery. It's a full-stack solution.
Software reducing the load, hardware managing the flow.
Yep.
So let's synthesize this for everyone listening. We started with a camera on a tree that was basically doomed to fail because of the energy wall.
We analyzed the data flow and found that structural barrier, the fact that deep learning expands data before it shrinks it.
Which makes traditional offloading impossible. So we applied co-design to prune the network and crush the data down to a 1-bit binary mosaic.
Saving 17 times the energy.
Then we used the QCNet on the server to reconstruct high-fidelity reality from that noisy mosaic, proving we don't need perfect data to get perfect answers.
And finally, we wrapped the physical board in an AI PMC to monitor the heartbeat of the battery and prevent electrical failure.
And suddenly that smart world isn't just some sci-fi movie intro anymore. It's actually buildable. It's sustainable. It really forces you to rethink the value of data. We are obsessed with lossless quality, 4K, 8K, raw files. We hoard pixels. But this suggests that less is more. provided you have the intelligence to interpret it.
It suggests that intelligence isn't about hoarding information, it's about knowing which pixels you can afford to throw away. And it turns out you can throw away almost all of them if you really know what you're doing.
Which brings me to a final thought I wanted to leave you with. This whole time, we've been talking about teaching machines to see. The thesis proves that a machine can perceive the world perfectly well using just 1% of the data, this one-bit map, as long as the brain on the other end has strong priors or expectations.
Right. It relies on context.
It makes you wonder about human vision. Biology tells us our eyes aren't cameras. We have a very high-resolution center, but massive peripheral blind spots and low-res areas. We aren't seeing a 4K stream. We're seeing a compressed, shaky signal.
That's a profound parallel. You're absolutely right. Our retinas are the resource-constrained edge nodes. They send compressed, imperfect signals to the visual cortex.
And our brain is the server, running a massive reconstruction algorithm based on our memories and expectations to fill in the gaps.
So we don't stumble into walls because we are constantly hallucinating our own reality, just like the QCNet. We see what we expect to see.
We are the original split computing architecture. We've been doing one-bit inference for millions of years. And maybe by teaching machines to see this way, we aren't just making them more efficient, we're making them a little more like us.
That's a great way to put it.
A one-bit insight for a complex world. Thanks for joining us on this deep dive.
My pleasure.
See you in the next one.